Welcome to the Explainer. So, if you're prepping for the TEAS exam, you already know the science section can feel like, well, an absolute beast. Let's be real. Staring at a massive textbook, trying to memorize every cellular process since the dawn of time, it's enough to make anyone's blood pressure spike. But hey, don't worry. That is exactly why we're here today. Think of this Explainer as your low-stakes, highly engaging practice run. We're going to break down real question types and strategize on how to conquer them using logic and structured thinking. Okay, let's take a quick look at our agenda for this categorical deep dive. First up, genetics and cell biology. Second, chemistry and conversions. Third, anatomy and physiology. And finally, some absolutely crucial test prep takeaways. Let's get right into it.
Section 1, Genetics and Cell Biology.
We're kicking things off by looking at the microscopic building blocks of life. Question 4 asks, which of the following types of mutations will result in the codon reading frame being maintained? Your options are 1 nucleotide deletion, Frameshift mutation, 2 nucleotide insertion, or substitution mutation. Feel free to use the interactive pause button and stop the explainer right here if you want to try solving this one yourself first.
So, the absolute crucial point here is knowing exactly what these terms actually mean. A codon reading frame is read in groups of 3, right? Highlighting your vocabulary is key. If you insert or delete nucleotides, like in options A and C, you mathematically shift that entire triplet frame down the line. And option B literally has frameshift in the name, so we definitely know that one doesn't maintain the frame. That leaves us with option D. A substitution mutation simply swaps out one base for another. Because you aren't adding or subtracting the total number of bases, the reading frame stays perfectly intact.
Let's see how this builds into broader cellular biology with question 6. This one asks, which of the following structures is present in both prokaryotic and eukaryotic cells? And your choices are Golgi apparatus, endoplasmic reticulum, chloroplast, and cell membrane.
What's really interesting here is how we can use the process of elimination to find the answer without even breaking a sweat. You know, eukaryotic cells are the complex ones. Think animal and plant cells full of specialized membrane-bound organelles. Prokaryotic cells, like bacteria, are just much simpler. So we can confidently cross out the Golgi apparatus, the endoplasmic reticulum, and the chloroplast, because those are complex organelles found only in eukaryotes. That proves that both simple and complex cell types must share the foundational boundary layer, the cell membrane, which is option D.
Section 2, Chemistry and Conversions.
Moving right along, question 5 asks you to identify the balanced chemical equation from the 4 options provided. Give this explainer another quick interactive pause to literally count the atoms on both sides of the arrows before we break it all down together. And this brilliantly illustrates why a simple counting table is going to be your absolute best friend on test day. In a balanced equation, the number of atoms you start with literally has to equal the number you end up with. By tracking the inputs, or reactants, and the outputs, or products, we can test each option. If we look at option D, we have 2 H2O molecules on the left, giving us exactly 4 hydrogens and 2 oxygens. On the right side, we have 2 H2 molecules, that's 4 hydrogens, plus an O2 molecule, which is 2 oxygens. It's a perfect match on both sides of the arrow, making option D the correct balanced equation. Up next is question 7, which tests your metric system fluency. It asks, which of the following is equivalent to 2.5 kilometers? Now, doing unit conversions quickly and accurately is a foundational math skill that is absolutely essential for nursing and basically all allied health fields. Rather than just guessing or, randomly moving decimal points around, you really should systematically map out the steps. Step 1, convert your kilometers to meters. We know there are 1,000 meters in a kilometer, so 2.5 kilometers multiplied by 1,000 gives us 2,500 meters. Step 2, convert those meters into centimeters. There are 100 centimeters in a single meter, so we multiply 2,500 meters by 100, and we find the equivalent is exactly 250,000 centimeters. Following this structured math lands us confidently right on option A.
Section 3, Anatomy and Physiology.
Now, how do we apply all those microscopic cell concepts and chemical principles directly to the complex macroscopic systems of the human body? Well, question 8 asks, which of the following is the primary reason smoking can lead to high blood pressure? Take a quick pause to read through the 4 options and try to isolate the key medical terminology in each statement.
So the crucial point here, once again, comes down to really knowing your vocabulary. The core of this question is the definition of vasoconstriction. Vaso refers to blood vessels, and constriction means narrowing.
When your blood vessels narrow, the exact same volume of blood is being squeezed through a much smaller pipe, which actively forces your blood pressure to rise. Understanding that this terminology simply means narrowing blood vessels perfectly explains why option B, noting nicotine's mechanical effect of arterial vasoconstriction, is for sure the correct physiological answer.
Finally, let's take a look at question 9. This one tackles the critical concept of homeostasis, asking what happens when blood pH decreases below its normal range. This is a classic critical thinking question, actually, because it requires understanding cause, effect, and the body's natural compensatory mechanisms.
Let's break this down logically. First, remember that a decreased pH means the blood has become more acidic. It has an excess of hydrogen or H+ ions. Since the blood is already way too acidic, releasing more H+ ions would just make the situation worse. Therefore, we must immediately eliminate options A and B because they both describe releasing H+ ions. To restore homeostasis, the body has to bind or basically soak up that excess acid. This leaves us with option C, bicarbonate ions in the bloodstream binding to excess H+ ions, as the accurate biological mechanism to raise the pH back up to normal.
Section 4. Test Prep Takeaways.
You've successfully made it through the gauntlet of varying scientific disciplines today. Taking a step back, you'll probably notice a common thread in how we tackled every single problem. The biggest takeaway from these source questions is that isolating core vocabulary and actively proving why wrong options don't fit is a far more powerful test-taking skill than just blindly jumping to what you hope is the right answer. Also, grouping your study topics categorically, just like we did today, ensures you're building a strong foundational context for your knowledge, rather than just memorizing a totally random assortment of flashcards.
Which brings us to our final thought. Are you actively breaking down questions, or are you just passively memorizing facts? I challenge you to apply this structured active breakdown method to all of your future TEAS prep. Use the process of elimination, map out your math steps, define the vocabulary. If you study with this kind of intense focus, you aren't just practicing, you are practically engineering your success. Keep up the hard work, keep asking why an answer is correct, and go conquer that exam.